So now we have everything in place to introduce the tool we need to make quantitative calculations of wave functions in quantum mechanics. Newton's second law of quantum mechanics, the way in which we determine wave functions, given some potential that a particle finds itself in, is the Schrodinger equation. The Schrodinger equation was essentially guessed by Schrodinger as a way to give results consistent with what was known of atomic physics at the time, and it's not even correct for example, relativistic speeds or electromagnetic interactions. Nonetheless, it will be just fine for all the calculations you're ever likely to encounter in nanoscience, and here it is. It's a little fierce looking for those of you unfamiliar with partial differential equations, but let's go through it. The first term here is minus h bar squared on 2m. M is the mass of a particle. It's a Schrodinger equation for a single particle of mass m. Planck's constant squared occurring. The h bar is Planck's constant divided by 2 pi. So you'll often see this h bar occurring in quantum mechanical expressions. This here is the second derivative of the wave function with respect to space, and the little curly d's mean a partial derivative so that we would ignore any time dependence in this term. Here is a potential which might depend on space and time, multiplying the wave function, and that's equal to I, the square root of minus 1, times h bar, times the time derivative of the wave function. Now, very often we will have potentials that are independent of time, in which case the wave function can be written as a product of a spatially dependent part and a time-dependent part. To see this, let's just substitute this product in the Schrodinger equation. So we're going to write for big phi of psi of x and t, a little psi of x times phi of t. When we operate on this with the second derivative operator here, it's a second derivative with respect to x. So this will operate on this part, but not on this part. To the second derivative operator in x partial derivative, this appears as a constant. So this will just return d2 psi dx squared times phi of t. This next term here is not a function of time, and it's just multiplied by the wave function, and so this will be phi of x times phi of t, and then over on the right we take the derivative with respect to time. This will only operate on the phi part of the wave function, phi of t, so this will be multiplied by phi of x. So if we divide both sides by psi of x, we take out the psi of x occurring on this side, and we bring a 1 over psi of x over onto this side of the equation. We then divide both sides by phi of t, and we take out all the phi of t's on this side and bring out a 1 over phi of t on the right-hand side of the equation. So now we have an equation in which functions purely of x on the left are equal to functions purely of t on the right. There is only one way in which this statement can be generally true, and that is if the function on the left is equal to the same thing as the function on the right, and that thing does not depend on x and does not depend on t, i.e. it is a constant. So let's just write down then the right-hand side of the equation here. And we're going to call the constant E. There's a reason for doing that, because when we rearrange this equation, and we do it in the following way, we see that the solution is an exponential. Now, we will recognize an exponential of this form, which we could rewrite and I'm going to rewrite this in the following way, as simply the expression for a sinusoidal or cosinusoidal wave, where we have used, but that is simply Planck's result for the energy of a sine or cosinusoidal wave, i.e. a photon. So we see then that the choice of energy, at least for the case of a photon as this constant, is the appropriate choice, and if the potential is independent of time, the right-hand side of the Schrodinger equation is simply equal to the energy. So this leads us then to the time-independent Schrodinger equation, and this is stated here, and it now looks a lot simpler than the time-dependent equation. So the second derivative of the wave function, which is now purely a function of position, of course we'd have to write out other terms in 3 dimensions, and there is the Schrodinger equation. The psi of x on the right comes because before we had this whole thing bracketed and multiplied by 1 over psi of x. Very often we simplify this equation by taking out the psi of x and writing this part by the symbol h, the Hamiltonian operator. It's an operator because, of course, it doesn't mean anything until we multiply by the right, and that's important, by psi of x, in which case we recover the Schrodinger equation. So in terms of the Hamiltonian operator, the Schrodinger equation, the time-independent Schrodinger equation, becomes just h psi is e psi. So if you were scared of partial differential equations, you can probably remember the time-independent Schrodinger equation as h psi equals e psi.